Okay, so you've got installers, 32-bit and 64-bit. This is everybody at this point. Everybody is hopefully using the latest version of Skyline. I guess we can double check that. If people get into Skyline and then do help about, then there is your help about should say 3.1.07382. If it doesn't, you might want to use one of these installers. Otherwise, you may find that there are some things that I do that you won't be able to do. So you could use these installers to update. Probably most of you have 64-bit computers and could install from the 64-bit. Otherwise, you just have those as for your own use. The thing about these installers is they won't auto-update, so you really would prefer to install off the website. And then we have this whole folder full of tutorials, which we got 3 Skyjams this week. This is the first one, and I sort of have preferences on what the other 2 are going to be, but they could be drawn from this based on sort of feedback from you guys after this session. But the first one we're going to do is this group studies one. So if everybody would just grab the group studies folder and drag it to your desktop. So for me, that's like this, and then it will start copying. And it's not a huge amount of data, so it should copy pretty quickly. But just get that group studies thing on your desktop. I'm going to try to go through some slides pretty quickly, and then sort of heavily focus on actually using the software and sort of give you some ideas of how I find is the optimal way to use the software. And I've checked this with a lot of people who use it a lot, and they also feel that that these are some of the most effective ways of using the software. So I guess, yeah, so what is a Skyjam? It's something that I came up with at the course at the University of Washington. I kind of looked at the schedule and I went, there's not enough Skyline on the schedule. And so I started these Skyjams at 8 a.m. in the morning. So at the UW course at least, you had to be really dedicated to actually even attend a Skyjam. You had to wake up and be at the class at 8 o'clock in the morning. But they've been pretty popular, and that first time around, it went from about half the class showing up at 8 a.m. to by the end, most of the class showing up at 8 a.m. And then this year around, everybody just started showing up at 8 a.m. So we've now integrated them into the class. The idea is that the tutorials you've been doing so far are really, really great and provide you a great base foundation of using Skyline, and hopefully these Skyjams then sort of take you up to the next level, so that when you go home, you are completely above the rim with Skyline, and you're impressing your colleagues like this. Between the legs and completely above the rim for a slam dunk. Okay, so that's what a Skyjam is, and hopefully we're gonna do one in a second. So this Skyjam is focused on some work that we did pretty early when we had started Skyline around this idea of method refinement. And so in targeted proteomics, unlike DDA, in shotgun proteomics, where you're frequently collecting data and then you're sort of stuck with that data set, and then you analyze it, and there's not really that much of an opportunity to go back and retry it, after you've learned something. With targeted proteomics, we're frequently starting with what we've learned from a discovery experiment, a shotgun experiment, sort of putting it into this funnel here, which is beginning the cycle toward a really robust, highly repeatable quantitative assay. And originally, when I was working with the clinical proteomics technology assessment for cancer organization that was funding Skyline, we were thinking about clinical trial assays. So how do we get from these discovery experiments down to something that could actually be taken into a clinical trial? And what we came up with was this idea of targeted method refinement, and this is, this funnel was what Skyline was designed to be. So we were taking not only just results from DDA experiments, but also carefully crafted retention time libraries like the IRT libraries that you guys have been working on, spectral libraries, sort of broad measurement methods, and then just all kinds of previous measurements, and then taking them through these targeted method refinement cycle. And the targeted method refinement cycle looks like this, where you start out by building a method, run the method on your mass spectrometer, evaluate the results using Skyline, actually use Skyline to build the method too, and then refine. And that funnel, you would go through this cycle many times, and we do now. We're doing this in the McCoss lab, and I'm sure that people here at the Aerosol lab are doing this as well. And eventually you end up with a much better method for measuring what you're trying to measure. And so that refinement, these refinements you can be looking at various things, such as just what's the relative abundance, trying to figure out which peptides you want to measure. What are the 3 most abundant peptides for your protein? Tina said for the absolute label-free quantification, that's important to know. Well, you could find that out with Skyline and targeted measurement. Measurability, what's actually going to be measurable in your sample matrix. That degradation, I showed you that was a problem, and I'm going to come back to that in another slide in a second. Digestion efficiency, what is happening with digestion if you're going to put your proteins into trypsin, or some other protease. It's sometimes important to know the digestion mechanics. And then doing scheduling and optimization of parameters like collision energy. So we're going to be looking at this. It's a label-free experiment where there were 14 salt-sensitive rats, 7 of which were given a low-salt diet, so that's the control group, and then 7 of which were given a high-salt diet, which eventually led them to heart failure. They were then executed, and from them it was harvested their blood, and we used their plasma for this experiment. So, and we chose to target 109 proteins reported in literature to be related to heart disease. So our hypothesis was that we would be able to measure differences in these 109 proteins because they'd been reported in the literature. And we had some pretty extreme differences between healthy, low-salt rats and other rats that had gone all the way to heart failure. So we had this idea of phases of refinement that we could start out just by figuring out what peptides might be detectable, and we did this all in SRM. I think today we would do this initial detection phase probably using DIA or some other more suitable method than SRM, because with SRM it took us 151 unscheduled methods just to try to figure out what might be detectable, and I think we have better methods for doing that now. But it was, our thought was, at the time, a lot of people were doing a lot of targeted proteomics with synthetic peptides, and we were like, well, how far down this refinement cycle can we get before we have to actually order synthetic peptides because they're expensive. So we started out with we decided we're just going to measure everything for these 109 proteins, all potential tryptic peptides, and their entire Y-ion series in an SRM measurement, and then we would come up with what seemed to be detectable, even if we were wrong, it might turn out that when we ordered a synthetic peptide, what we thought was a detection of our peptide might turn out it wasn't a detection of our peptide, but that kind of didn't matter. In the end, we generally could only find one thing that could have been a detection of our peptide, so we just kept all of those. And so that led us to, so this is the entire unrefined method in Skyline. Skyline was fully capable of generating the y-ion series from y3 to yn minus 1, and creating this large method which we measured in 151 sample injections. That initial detection phase led us to finding 49 proteins for which we had any hope of measuring without further sample preparation. So in the very simple, probably depleted plasma preparation that we did, we found 49 of the 109 proteins. And if we wanted to find more, we would probably have to change our sample prep. And then we found 135 peptides that we thought that we had some evidence of a peak that might be that peptide, and 780 transitions for those. And then we used 6 scheduled injections to do retention time scheduling. And then this is the Skyline scheduling view. I don't know have you guys seen that yet? Yes. Okay. So this is for that particular method, where you can see that a 4-minute window. This is on an older. This was on a TSQ Quantum Ultra, so an older instrument where we really felt that going much above 75 or 80 transitions per method would lead to, that you had to stay down below that in order to get quantitative results. What I'm hearing now is that modern mass spectrometers can do actually hundreds of concurrent transitions. So if you have a Quantiva or similar, the 6500 from AVSciX, or the Shimadzu, or any one of those triple quadrupoles, can now do hundreds of transitions. So that would allow us to probably, with a modern mass spectrometer, we could have measured a 10-minute window and had no problem. But we were trying to stay down below 70 or 80 or so, and so you'll see that we used a 5-minute window, and you'll see what impact that had on the data. So the experimental data is this rat plasma experiment measured by Daniela Tomazella in the McCoss lab at the University of Washington. 14 subjects, 7 diseased, 7 healthy. It was measured in technical triplicate, and you're going to be working, this is the data set that you just copied. The method design was proteins from literature, no labeled reference peptides. There was very little spectral library coverage, so we went and we searched existing spectral libraries at the time, and they didn't really give us enough information to be choosing transitions, and that's why we chose to measure the entire y-ion series from y3 to yn minus 1, and then try refinement. So that then led us to, then our idea was, well, we still didn't need to order synthetic labeled reference peptides to do accurate quantification until we had determined that not only could we detect these things, that there was some probability of them being differentially abundant. So no point in ordering synthetic labeled reference peptides for peaks that weren't changing between our case and our control. So we took those 49 proteins, 135 peptides, 780 transitions. We measured them in a single method. Once it was scheduled, we could measure all of that in one method, and we did 42 injections, and that brought us to the data set that's the data set that we're going to analyze together in a second. So before we do, I just want to go over quickly that what I think those of us who've been practicing targeted proteomics for the last 7-8 years really feel pretty strongly about is that that whole refinement cycle I was talking about, and prior knowledge of your peptides allows you to, and your proteins allows you to measure them much more accurately. So I wrote an article for the U.S. HUPO newsletter, and one of the sections was, just becoming more familiar with what you're measuring, because I've seen people who spend a bunch of time on a set of targets, and by the time they're done, their confidence that they can measure what they're trying to measure goes up considerably. But so prior knowledge is incredibly important, and that's because there are a number of things about peptides in mass spectrometers that are very consistent. And so we can measure those physiochemical properties of peptides, or the things that are impacted by physiochemical properties of peptides, and then those measurements are powerful enough to be used cross-lab and cross-experiment, but they're also more powerful run-to-run, and we're going to see that in the tutorial we're about to do. So the two primary ones that I'm thinking of are relative ion abundance. So that, you've seen that we're using the relative ion abundance as stored in spectral libraries. We've talked about building chromatogram libraries on Panorama. But yeah, so the fact that we build these libraries says that this is a property that's incredibly stable, and we can take it, not only just to another instrument in our own lab, but we can send these libraries off to other labs, and the knowledge that we have gained from measuring MS spectra or prior chromatogram measurements and getting peak areas gives us this knowledge of relative ion abundance, and with chromatogram libraries, we can actually get relative ion abundance of the precursor ions, so the peptides, so we can know what are the most intense peptides for our proteins. But so that's incredibly stable, and so that means it's more stable if it's just staying on the same instrument run to run, and we'll see that. And then retention time. So retention time, again, is very stable, and IRT is this concept that we can measure retention times on an instrument and store them relative to each other, and then pull them out and use them on another instrument with a different gradient. But that also means that retention time is incredibly stable, run to run on a set of measurements taken on the same instrument. And then also optimal collision energy. We can, as Ariel explained, we can optimize further our method to use the optimal collision energies to produce the highest areas. We're working with multiple instrument vendors on ion mobility, which again, ion mobility is a property of peptides, which are extremely hard to predict. Nobody has a good predictor for it, but it can be measured and stored and reused. Okay, so here is a first look at data. We're going to be looking at this live in Skyline, but these are some Skyline graphs just in front of you, just to start familiarizing yourself with these graphs. We're going to set this up in Skyline ourselves. These are two pretty important views. So on the top, we have the peak areas normalized. So we just see percentages of the total. And what you can see is that there's a lot of stability. This is giving you a view into the relative ion abundance of the fragments. And when you see these nice, horizontal stripes of color, that means that, things are working well. The likelihood that we're measuring the same thing over and over again goes up. It's really high. Again, if we look at the retention time plot and we see, I showed you that the best chromatography I've ever seen, where it was just straight across, very, very little deviation at all. Here we have a little bit more deviation. We have this one little thing that kind of sticks out. But if we were looking at all of the peptides in this document, and you will be looking at a number of them, you'll start to see that this thing always sticks out a little bit. So if we had IRTs in this run and we aligned by IRTs, a lot of this variance would even just go away. But we can sort of get used to this level of variance and expect it from run to run. And there's just real, we're talking about, a minute. Very little is much further than a minute away from any other run. So that's very, very good consistency. So okay, so let's go back to this top thing here, and who can tell me something that they notice about this? Sure, tell me. Yeah, so the variance over here, and these are the samples in triplicate. So you can see the subject number is here. The healthier diseased is the D or the H, and then you can see we have rep 1, 2, 3. So this is logically organized with all the disease on the left and all the healthy on the right. That's not the way they were measured necessarily. It's just a logical ordering, and the variance over here is much greater than the variance over here. And so I'm about to, next slide, I'm going to denormalize this data. What do you think you're going to see based on that? Weak signal where? Yeah, so we're gonna have less signal over here. And sure enough, this is what happens. It's, looking on a linear scale, on a log scale, you'd be able to see the both. But on a linear scale, the peak area in the diseased cohort is almost invisible at the level of the signal in the healthy. And this is for this one peptide of the protein haptoglobin. The other peptide that we measured from haptoglobin has a similar pattern, and that strengthens the hypothesis that this is actually a good indicator of what we're measuring between these two groups, and it might be one of the stronger biomarker candidates in this sample. So now let's look at another example. Yes. So in this case, there's no normalization going on at all. So these are just raw peak areas. We will go over a little bit of normalization, but yeah, this is raw peak areas, yeah, okay. So onto this one. So what do you see in this one? Pretty messy, right? but not like, so the first course I taught with, we decided to use this data set. And this data set didn't actually end up getting published, which maybe tells you a little bit about the data set. But I think it's great to actually have a data set with some problems, because perfect data sets are often really easy to look at, and you can learn a lot from data sets that have problems. But so is it a complete and total loss? Like, I think if all of the data looked like this, we would just throw this away and say, well, this is not a quantifiable peptide. Yeah, the healthy still has it's not quite as good as the healthy on this side, for this one, but it's pretty stable, and the retention times are pretty stable too. And so I was the one who integrated this. This is my best attempt to get some sort of signal in all runs that maybe approximates what I'm measuring over here. And then now the great thing about Skyline is very easy to drill in and see like, oh, well, what did you do, and how did you come up with that? And boy, it doesn't really look like this almost in any run. So let's take a look at then if I denormalize, we can see that there's again very little signal in the disease group, quite a lot of signal in that, or not, but a lot more signal in the healthy group. And then the other peptide for this protein, strangely, is going the other direction. Not very strongly, but there's more signal in the disease group than there is in the healthy group. Not enough that this would be like a biomarker candidate, but enough to sort of call into question whether we're actually measuring two peptides from the same protein. Although certainly two peptides from the same protein can go different directions based on lots of different possibilities like PTMs and chemical modifications. Okay, so then if we, very easy to do this in Skyline. If we drill into the chromatogram level, we can see that most of the healthy candidates look like this, which, while it's not a beautiful peak, and it might be very close to the lower limit of quantification, but it definitely, that is a peptide. And it's repeated over and over again, and so I feel pretty confident that in the healthy, we're measuring a peptide. Whether we're measuring exactly this peptide, I can't say. But if I wanted to say, what would I do? Yeah, just order a synthetic peptide, and then that would tell me. And if this turned out to be the best biomarker candidate anybody's ever seen, would I care whether it's this peptide? Not necessarily. So, if as long as I'm measuring something consistent, this may still be a useful discovery. So then looking over at an example of the diseased group, this is what I've chosen to integrate. it's really hard to even see that these are co-eluting, but at least this the most intense thing, it's down at 100, where this is up in the thousands. But the most intense thing is my transition, my Y6, and then I'm getting sort of somewhat similar signal over here. But this, you never would just integrate this on its own. If I zoom out to see the entire measured range, there, I could integrate the entire measured range here, and I wouldn't get as much signal as I'm getting over here. So I have to choose something over here, or I have to take on the theory that maybe I just didn't catch this peak in this retention time window. So maybe the peak is actually outside the retention time window because of some sort of retention time shift. Those are the two possible hypotheses. Either there's something in here, or it was completely not detectable, and choosing something that's just a little bit of signal is a good approximation of not detectable. I would be overestimating how much contribution there was here, which I'm not really worried about, because I'm seeing this huge change, and by integrating anything, I might be overestimating how much signal there is of this peptide in the disease group. But anyway, so at this point there is the question of like, okay, so did the peptide just shift outside my retention time window, my scheduling window? Yeah. I manually said, I don't know what Skyline would probably pick something that looks to it more like a peak, and not necessarily pick that. Yeah, so I had to go in and actually manually choose this. So then a useful feature in Skyline is that you can order. So we've been looking at this logical ordering with all the diseased on one side, all the healthy on the other. It's very easy in Skyline to just order everything by acquired time. So this, I can actually see how the data was acquired. I showed you this same data in my first presentation for a different reason, but I had been told over and over again by Mike McCoss and Daniela Tomazella how important it was to randomize, and how in early experiments they'd failed to randomize, and how that had really caused some problems. And so my heart kind of sank when I looked at this data and saw that it wasn't randomized, because they had said, oh, this is going to be, it's randomized. But you can see that it's 102, 103, 108, and at least it's in cycles, right? So, but it's always disease before healthy, disease before healthy, disease before healthy, and everything's exactly in the right order. And so when Olga Vitek is here tomorrow, she's going to explain to you why you really need to randomize. And it would have been a lot nicer if this data were randomized. But since it's measured in 3 cycles, it's extremely unlikely that this peak is just moving outside the retention time window and then back again, out and back again. If these were measured, all disease then all healthy, then maybe I could believe that, and I might have to go, look at this more closely and figure out whether they were acquired on different times and maybe different chromatography. But at this point, seeing this acquisition order, I feel pretty confident that there should be something to measure in this area for this peptide every time. And so then, just as an example, this is what a truncated peak looks like. When things are shifting outside the retention time window, we're going to see more of these when we start looking at the data in a second. This is what it looks like. You frequently can see the peak of interest, on the edge of your measurement window. It doesn't just like hop out and then hop back in any time that I've seen. So I feel pretty confident that there is actually something going on here. This might be a reasonable biomarker candidate. I would probably take it to sort of my next phase of investigation, and that's what refinement's all about. Okay, so then other things that we might be refining for is to find these problematic peptides, right? So we want to, at the McCoss lab, we are now frequently measuring. We've got a protocol that says to measure, I think it's 48 hours or 72 hours between measurements. So every peptide that we're thinking of including in a quantitative assay, we will measure 42 hours or 78 hours apart and see if we see appreciable degradation. So like we expect very, very close CVs with a measurement over 48 hours, I think. And we don't want to see something like this where this is a 200-fold degradation. We would just throw this out as a candidate for quantification. Yeah. Sorry. Trypsin digested peptides. Yeah, it's a trypsin digested sample. And I'm sorry, what's the... These are tryptic digested peptides. So there's no synthetics in this experiment at all. No labeled peptides, no synthetics. We just start the whole point of this experiment was just to see how far could we get without ordering and without paying. Mike McCoss, we have a lot of instrument time. We don't have a lot of money for synthetic peptides. So the idea was to see how far can you get in a quantitative assay before you actually order the synthetic peptides. And so yeah, this is and this, we're pretty sure that this is actually degradation in the autosampler. We tried a bunch of possible PTMs on these peptides to see if we could figure out whether there's like some sort of deamidation or something like that was causing these things. We've never been able to catch one where we really feel like we understand what is happening with the degradation. But if we pull the same sample out of the freezer, it'll go right back up to this level. So it's time in the autosampler for a lot of these. That's a strange one. So another thing that we look at is digestion kinetics, and so this is a time course of experiment on digestion. So how long the sample is left digesting in trypsin, and when we see something like this, this is not a good candidate for quantification because we don't really understand the digestion kinetics. It goes up and then comes back down, and so. This makes it very sensitive all of a sudden to the amount of time it gets digested. And what we'd really much prefer to see is something like this that kind of goes up slowly and levels off. Ideally, we'd see it go up really quickly and level off. But we want to see something that reaches a sort of stable level of digestion and stable abundance at a certain period. And then knowledge of that will help us to understand what we need to do in terms of sample prep. And that's it for the slides. So let's go. Oh, sir, questions? Mm-hmm.
There's a problem here. The file pops up.
Mm-hmm.
There's some kind of feature you tend to add. So to see the data when you have multiple.
Well, I mean, yeah, we definitely would like to add more features, but I'm also going to show you how to deal with it with 42 samples and sort of this SkyJam was sort of developed in response to people who were talking about like. You have to look at every chromatogram, every transition, and you don't. Like even with a tool that doesn't have an automated thing that pops things up, you can go through the samples very quickly. I've processed this entire data file as best I think I can process it in about an hour. So 42 replicates, 100 and something peptides. I think that the rate of processing, I would say, for somebody who's proficient in Skyline should be about 1,000 peptides in a day, with just, and up to 100 samples, So I'm going to teach you techniques to do that.
It would be good to have a computer do that instead of you.
Yeah, absolutely. Yeah, well, it's much less if you have. Do you have labeled synthetics? Yeah. So then it should be much less. So this is for a label-free experiment. with labeled synthetics, the data sets that I see, there's just, you can certainly do more things to check ratios between your lights and heavies, and Skyline will just pick way better. Um, so anyway, let's go ahead and look at this and see what we can learn. It's a really good way of just interrogating the data and seeing what you can figure out. I have found that people can send me data sets and I can frequently be telling them stuff about their data in 15 minutes that they didn't even know. All right, so we all have, so let's just go to open. And then everybody should have on the desktop an a group studies folder, inside of which there's a heart failure folder, inside of which there is a raw directory and a rat plasma sky.zip, and so do not open that. If you open that, you're going to be just way ahead of everybody, because that's the final process thing that I processed. I mean, so at some point in this SkyJam, we're going to do a little Julia Childs and pull out the completely baked thing and take a look at that. But we're going to start by going down into this raw folder, and here you'll find a ratplasma.sky. And so open that. So this doesn't have any data in it. It's got a library match view. If you click on the first peptide, you can see the spectrum from this peptide. You can see that it comes from a library called RAT-NIST. Okay, so let's go back. It's fine. So if you pull group studies onto your desktop, go down to heart failure, go down to raw, and then no. Down in raw? Are you all the way down in raw and not? You got it. Okay, so double click that and open it. Where are you? Yeah, I think that's not it. So go down to heart failure. Go to raw. What are you do not have? Go to Skyline. Okay, click open and desktop. Where's your group studies? Heart failure. Raw. There you go. All right. So hopefully everybody's got it now. You maybe opened you opened what I said not to open. But that's okay. Just go file open again, and if you get to the right place, you'll be all set. And Tina will help you. So she just opened the fully processed data file, which we're all going to be opening together lately. It's not a problem. She can come back to it. All right. So if when you come to this spectral library view, you don't see the blue B ions, you can turn them on by right-clicking on the graph, and then clicking B ions. I just turn them off. I can turn them back on. I can also choose charge states 1 and 2, as I have here, and then this is what that graph looks like. If you select through these transitions, Skyline will highlight each one. So you can see that the set of transitions that are currently chosen were not chosen from this library the way you have been working with things recently. These are the transitions that to Daniela appeared detectable when she did the detection level experiment. So you can see that the most intense this Y10 is not in that list. Not sure why, but so you, and but so it's not. You would expect that maybe it would be 1, 2, 3. It would be Y10, Y11, but in this case, that's not what we came up with. This next peptide, there is no library spectrum. As I said, the library coverage was very spotty. It still is pretty spotty, but by the time we had this document, we had found spectra for new peptides. So some of these peptides have spectra and some don't, and it's not really important for this experiment. So we're going to actually close this library match view right now. And we're just going to go ahead and import the data. So file, import results, and then we just have single injection replicates. I told you that we have 42 runs, that each run measures this. Who can tell me how many peptides are in this document? 137. So we got 137 peptides, and we're able to measure them all with a single scheduled run. So just click OK for single injection replicates. And here are the 42 runs. In this case, they're all .mzml files. They started as .raw files, and I converted them to .mzml, and that's purely because the MZML imports a lot faster than the raw files, and so in a tutorial setting, this just goes a lot quicker for everybody if we use the MZML files, but Skyline can deal with all the raw data formats. You don't have to convert to MZML or MZXML or anything. Skyline can deal with all the raw data formats for all the instruments. How did I convert them? I used ProteoWizard, so there's something called ProteoWizard, and it has a MS Convert GUI. So you can go and, so let's see, I probably have it on this machine. If I go, let's see, absolute quant maybe. So this is a set of raw files. If you have MS Convert GUI on your machine, you can right click, and I don't have it on this machine. So if you have it on your machine, you could select these, right click, and then it would say run MS Convert GUI. And that's how I did it. And then MS Convert GUI will pop up with a bunch of options, and you can run the conversion. So, and yeah, just search for ProteoWizard to get that. Okay, so we've got this. Let's get it going, because it will go pretty quickly on my computer, but I have a pretty fast computer. So one of the nice things about SRM data is it's small and it imports very quickly. When we get to DIA data and other sort of full scan data formats, there are a lot of advantages to those formats, but they don't import as quickly, and they're not as easy to hand around. So okay, so this thing is now importing. I can work now while it's importing. I can hide this view, and I better hide it quick because it's going quickly. I can hide it, and anytime I want to get it back, I can go down to where I can see the progress still happening down in this little bar in the status bar, and if I click the button next to it, that window will pop back up. So, but I don't need to have it around, and I can hide it and continue working. So I'm going to show you what I think is one of the more effective layouts for processing data like this. Where you are going to do some manual inspection of your data, and you're going to, I would say even as we have better automated tools, it's incredibly useful to drill in and inspect things, and not just rely on this thing that spits out a matrix of information for you. So everybody grab the title bar of this targets view. So this blue title bar here, if you grab it and pull and just sort of click down, drag the mouse, you'll get a blue box showing this floating blue box up above the window. Once you've got that, you can release, and that just pulls the targets window off the main window. Then if you grab the title bar of retention times, and if you move it around, you'll see that it shows a blue box, and we can just move it floating like that anywhere we want. But what we want to do, oh, sorry. If you don't have those retention times, go View, Retention Times, And what we want is the replicate comparison. So, and then while you're at it, also view, what? Well, if it doesn't look like that, it's probably because you have a different peptide selected or a protein selected. If you have a protein selected, you'll see nothing. If you have a different, I have this LGG peptide selected. That's the third peptide. So if you want it to look exactly like mine, just select LGG. And then also you can do view peak areas, replicate comparison, and that should give you both these windows sort of floating up above, unless you've already previously docked them to something. And what we're going to do is take this retention times window and drag it down to the bottom, and you drag. What you're going to do is you drag until your cursor gets inside this little rectangle indicating a dock at the bottom of the screen, and then you'll see that all of a sudden the blue rectangle indicating the retention time window sort of clicks and into place at the bottom of the screen and shows you this blue rectangle that goes all the way across like that. And that's completely dependent on whether or not your cursor is inside this rectangle. Okay, and then you can release, and you'll see that it gets docked to the edge of the window. And then we're going to take the peak areas, and we're going to make it share the same space with the retention times by dragging it down into the retention times, the cursor into the retention times window, and you'll see that this cross appears, and we can then make peak areas share the same space with retention times in various different ways. What we're going to do is choose the one on the right side, so that it looks like this. The blue box is to the right of the retention times, and then you can just release, and now you have side by side the two windows docked side by side, and you can see them both. And then next, we're going to take the targets window and drag it again and put the cursor in the rectangle to the left so that it's docked on the left edge, like that. And so there are other windows in Skyline that behave like this. You'll find it's very flexible. This is docking windows. I'm a co-inventor on this patent at Microsoft. So if you hate these things, it's my fault. I like them enough that I put them in this project as well. But it makes it very flexible and how you can lay out your windows. And now I guess I think I'm going to run around. Oh, actually, let's do one more thing. So let's go to View, Arrange Graphs, Grouped. So View, Arrange Graphs, Grouped, which brings up a form like this. And you remember that this data is collected in triplicate. And so we're going to tell Skyline to split this document area with the tabs in it up into 3 panes so that we can see all of the sample, all of the data for a single individual in one view. And actually, let's quickly, we can do View, Arrange Graphs. If you cancel out of there, View, Arrange Graphs tiled. If we had a lot more screen real estate, that might be interesting. In this case, it just gives us a whole lot of blank boxes because Skyline, there's just not enough room to graph in here. And so if you ever get into a state, it can be a lot less severe than that one. Like if we put Skyline in a state where, or we put the graphing package that Skyline uses in a state where it can't draw the graph, basically there's no graph region anymore. It just blanks everything out, and that can be kind of startling to people. And I've gotten support requests about, why am I getting this blank box? It just means that you've got to give it more space in order to see it. So let's go now back to we can do View, Arrange Graphs tabbed, and that will put everything back the way we had it before. And then finally View, Arrange Graphs grouped, and we're going to say that we want 3 group panes. We want to distribute the graphs among the groups, and that's going to cause Skyline to sort of deal them out like a deck of cards. If you hover over this control, it'll actually say graphs are distributed among the panes as if dealing a deck of cards. Unfortunately, not all forms in Skyline have this, but some of them do. And so if you hover over these things, sometimes they'll give you tips. We're going to use display. We're going to use display row. So we just want a row, and Skyline would probably do that even if we chose tiled. But just to force it, we're going to say we want one row of windows. We're going to sort them in the order that we have them in the document. So choose sort order document, and we're not going to do reversed order. So once your form looks like this, anybody not here yet? Okay, then click OK. Okay, so now the one trick here is that if you hadn't closed your spectral library, or you hadn't quite gotten any of these windows docked in the right place, they might have all of a sudden gotten mixed up in here. And that just means there's a difference between the windows with these tabs on the top and the windows with these title bars on the top. And so the ones with the tabs sort of participate in this document area space, and the ones with the title bars are sort of docked around the edges of that. And so hopefully everybody's looking like this. I'm now just going to kind of come and take a quick look at all of you. And people, like, raise your hands if you don't think you have this view at this point. Pretty good. Oh yeah, so you this is exactly what I was talking about. So all you have to do is just grab this and dock it over to the edge. So, and make sure that it has this title bar, and then you might just do that same command again. And there you go. Okay. Anybody else? Raise your hand if you don't think you quite have this view. So we'll talk about that all together. Yes. Okay. So here you're in the peptide comparison graph, and you want to be in the replicate comparison graph. Good job, everyone. It's looking pretty good. Oh, what? Oh, yeah. You want? Whoops. There you go. All right. Great job. Yeah. Yeah. So that's because it's got a tab on it, right?
Yeah.
So there's a difference between docking over here and docking here. And now if you do view,
Okay.
so you want to make sure you have a title bar instead of a tab, and then now you can rearrange and everything should be good. Yes.
What's happening with thematic areas?
Uh,
I don't know what I have done there. It's better
Why
to
is-
close and open again.
no. I don't know. Okay. You must have zoomed in. Okay, so you also have this. Let me just quickly. Oops. Okay. Yep. Okay. Good. We're all set. So let's go up to the very top. The very top peptide. Let's see what we see. Oh, one more thing. You'll notice that this legend gets repeated a lot. We've got this legend that tells us Y9 through Y3 in 5 different graphs on the screen. So I'm going to right-click on the chromatogram graph and turn off the legend, just so that I have a little bit more space to view things. And if I ever need a legend, I can go look at these other graphs. The other thing is we're going to switch into the mode where we're actually looking at that. So right now we can see the absolute abundances of all of our peaks, which is we're going to switch into that view sometimes. But right now we're going to switch into the view that I was showing in the presentation. So if you right-click on the peak areas view and choose normalize to total, that switches you into this view where you're seeing the relative ion abundances of all the peaks. All right, so what do we see on this first one? Yeah, kind of a mess, huh? So if you were to kind of just squint and look for a pattern, does anybody see any sort of pattern here? Is there anything that could maybe be a peak? I would say that, if there's anything, there's something around this, I'm seeing Skyline somewhat consistently, not very consistently, but pick something around 18.5 minutes. So I'm kind of interested in what that is. Actually, I can see over here, this is one of them. It's got a terrible dot product with my expected abundances. But one more thing is actually I'm going to zoom in. Yeah. So if I expand the peptide and look at the precursor, on the precursor level, if I expand it I can see the precursor, and then there's a dot product here. When I have more screen real estate, it'll also frequently put the dot products on top of the peak areas views and stuff like that. Are you looking at GILAD, the peptide GILAD? You don't have a library. Oh, yeah, that'll do it. So that is, so if you remove the library, that will do it. So yeah, this dot product what is the dot product a comparison of? Does anybody know what dot P is a comparison of? Yeah, to this reference spectrum. So if I go view library match, and I'm going to grab this and just dock it onto the edge here, and then I'll unpin it. So now I can kind of pop it out and look at it if I want to, and then it goes away when I don't want it. Yeah, you don't all have to do this, but if you want to, let's go ahead and so if I show that library match, go view library match, then I show it and I drag it off and then drag it and put my cursor over so that it's on the right side here. So all the way to the right, and put my cursor in there and then let go. And I want to have a library match with a title bar here. And then inside the title bar is a little push pin. And if you click that push pin, it unpins it, and then now you get a tab over on the side that allows you to sort of, anytime you put the mouse in there, it'll pop out a window that allows us to look at the library. So this peptide has a library match. Another place where we can find the relative ion abundance of the library is over on this very left bar in it down below here. So that shows me the relative abundance, and that can give me some clue as to what I'm expecting to see. So this thing here, D102 rep 1, actually has a fairly similar relative ion abundance. Well, it's got a 0.66 relative ion abundance dot product with my actual thing. But if I click on some of the other ones, when I click on, you can click on any bar here, and it will activate the tab for that bar. So if I click in the peak areas view, I can click on a bar and it will activate the tab, and I can see that. And then once I activate a tab, you can see the dot P value is changing. So the dot P value is per replicate, and the one that's showing up in the tree is, that's the one for the active replicate. If I also, don't everybody try to follow me, but I'm going to pull the peak areas off, expand it so it's a little bit bigger, and so this is if you're going to be working with Skyline a lot, this is a great excuse to go to your boss and make sure you have a really big monitor. I've seen people. I've gone to labs where they actually have special Skyline processing workstations where they have 2 monitors so that they can just look at a lot of data all at once, and they spread Skyline across the whole thing. And so it's definitely Skyline is very fast at displaying this data, and so if you want to sort of take in a lot of data at once, having screen real estate helps. So I'm gonna turn off the normalization for a second here, and I'm still not wide enough to, let's see, am I? No. So I have to be pretty wide to have the dot P values show up here, but when I get wide enough, I can see them. And so here you can see all of the dot P values, and they're generally not a lot better than 0.5, which is terrible, right? So that gives me no confidence that I'm measuring what I think I'm measuring here. But there is one thing that I haven't yet done that I probably should do before completely throwing away this peptide, which we're going to do in a second. So if you zoom into these retention times, so what do you see about that's sort of interesting about these retention times? Right? They're not solid blocks. We seem to be missing bars in the retention times. And that's an indication that Skyline is in what I call refinement mode. So we just got done with doing a refinement experiment. Skyline's still in refinement mode, and we want to put it into quantitative mode. And when Skyline's in quantitative mode, it will integrate everything. So when you have integrate these black dashed lines, those are the integration boundaries, and Skyline is calculating the peak area between those boundaries for everything that it's integrating. But when you look over here in this view, if you see red dots, those are things that Skyline has kicked out and said, and so it's kicking out a fair amount here because it's just saying, well, I don't really think these are the same, they're not co-eluding. I don't see evidence that these are co-eluding. And so in refinement mode, that can be a useful indicator that you might want to stop measuring these before you go into quantitative mode. But since we're going to be in quantitative mode, and presumably Daniela Tomazella has done some refinement of these values already, we just want to tell Skyline integrate everything between the peak area boundaries, and the way to do that is to click on settings and then click integrate all. And once you do that, you'll see that the retention time, the blocks for the retention times fill out. But as long as we're in this zoomed in view, I'm even going to zoom in a little bit more maybe. You can maybe see, well, I think I'll pick things that are really close to retention time so I get big. So you can see that there are these lines. There's a line across the middle, and then there are these whiskers also. And what these indicate is the line across the middle is the apex. The bars are the base, so full width at base. This is showing where the integration boundaries are in time. The retention time is the y-axis. Another thing to know about Skyline plots is if I put the mouse to the left of the y-axis, I can zoom by using the scroll wheel, or if you have a trackpad using two-fingered scrolling. And it's mouse-centered zooming. So if I put the mouse where I want to zoom, then Skyline will zoom there. So now I can expand that even a little bit more by putting the mouse to the left of the y-axis and zooming. And so this is not a very good matchup. So this doesn't look, like even without looking at the chromatograms, I can see that this is not a good co-eluding peak because the apexes are all over the place. the full width at half max, is also much wider and thinner in various places, and so I don't even have to look at the chromatograms to know that this is not a great example of a co-eluding peak. All right, so now to get rid of all this zooming, I've zoomed in both graphs now. I can right-click and choose Undo All Zoom and Pan. And then again, Undo All Zoom and Pan. And now I'm going to switch back to Normalize to Total. So I get this. And now I guess I'm going to say, yep, if you look at this pretty closely, if you click on some of these peaks down at this 18.5 in this 18.5 range, none of them are very good example. None of them look very quantifiable. Frequently, we're only seeing two transitions co-eluding, and which two transitions are we seeing co-eluding? Anyone? What are the two ions that we're seeing signal for? Y3 and Y4, and what difference does that make? Does it make any difference whether it was Y10 and Y11 or Y3 and Y4? Yeah, so those are not very selective ions. Y3 is just barely better. So Y1 is like is just K or R. Y2 is K or R plus some other amino acid, and Y3 is just slightly better than that. So it's not a very selective ion, and so yeah, you want to pay some attention to this. I've seen people present in the MacLean lab meeting and show something. They're like, "Oh, I thought this was my peptide," and then when I ordered a synthetic, I found out it wasn't. And if they're going on, just really low mass to charge ratio ions, if they've actually measured 6 and they're seeing 3 of the lowest ones, then that's a good indicator that this is not really the peak you think it is. All right, so we're going to go ahead and delete this one and move on. We spent enough time on that guy. All right, next peptide. Does anybody see? Does anybody see anything I should look at? What? Yeah, there's no library match in this case. So what would you look at? Would you go through every chromatogram? Yeah, the one that has different retention time. This one, boy, that really, it's 3 minutes away from everything else. It's probably not the right peak. So if I can just bring the cursor over it till it turns into a hand, click on it, and I can see that it's not in the it doesn't look at anything like the other peaks. So if I want to get over to where the other peaks are, I can right-click on the chromatogram graph for one of them and choose Synchronize Zooming. And I already have Synchronized Zooming on, but if you don't, make sure that you click it so that Synchronized Zooming becomes checked. And then if you just sort of wiggle your mouse, or wiggle your scrolling, or you can use Control, Click, and Drag to pan. So you can scroll using a scroll wheel or the trackpad with 2-fingered tracking, or you can hold down the Control key and click and drag to pan things. And whatever you do now, Skyline will synchronize the other view to it. And now we can see that there is something here that looks a lot like our peak. We just didn't catch it all. So this is a truncated peak. Our scheduling is maybe a little too narrow for this. And now we have two choices. We can either remove the peak entirely and say, yep, we didn't get a valid measurement of this peak, and we definitely did not get a valid measurement of this peak. Or we can integrate it like this, and Skyline will store a value that tells us that this peak has been truncated. And we can use that in a downstream statistical tool. But if you're not sure whether your downstream statistical tool handles this case, then the right thing is to remove the peak. And we can do that by right-clicking in the chromatogram, choosing Remove Peak. Yeah. I wouldn't. I think it's maybe accurate. It's maybe more accurate to I could integrate this, and then my data would contain a notification saying this is where the peak was, but it was truncated. So to me, it provides a little bit more complete information, but you can also throw it out, and I'm going to show you how to throw it out right now. So right-click on the chromatogram graph. There's remove peak and all, and we do that. And now we get a blank bar where we had that other bar that looked or that, and we lose that retention time. So, and now I'm going to say to undo that, and we'll do it the other way. So just click the undo button up here, and you'll get that retention time back. And now to integrate a peak, the easiest thing to do is to click and drag under the x-axis. So if we click to the right of the peak and then drag across all the way to the end, now we get this truncated peak with a 30.1 retention time. And let's now, Skyline does store information about the fact that this is a truncated peak, and let's go quickly see that. So if you go to edit, find, and again click show advanced, we found mismatched transitions and some other interesting possibilities here. We could look for no matching library data. So here we have quite a lot of peptides with no matching library data, and we could find them all pretty quickly by clicking this no matching library data. If you have anything in the find box, go ahead and clear it now. And then way down at the bottom, we have truncated peaks. So just click truncated peaks, and then click find all. And you'll get this lit, and then close the find forum. And you'll get a pretty long list of truncated. So we just integrated something truncated, but Skyline has clearly integrated other things as truncated as well. Right at the top, you'll see one of the things that we just integrated as truncated, which is this D108 rep2. If you double click on it, Skyline will activate the thing that we just integrated. You can see that there's also, for the same peptide, there is H159 rep2, which is also truncated. If you double click on that, you can see that in one case, Skyline couldn't, decided I don't really understand this as a peak. And in the other case, it said, oh, there's a peak, but it integrated a fully truncated peak. And it is truncated. So, okay. So let's close that. Click the close button on the find results. All right, so there's at least one or two more things that I might want to look at here before I move on to the next peptide. So who can suggest a next thing to look at? Yeah, so there's this one replicate that has quite a lot of Y5, a lot more Y5 than everybody else, and a lot more Y3. So click on that one, and again, you can see a very teeny peak next to a truncated peak, and I'm going to say that we're just going to integrate the truncated peak as truncated by clicking beneath the x-axis and then dragging and releasing. And I would say that now we're pretty close to being done with this peptide. The one last thing I would probably look at is this one way on the end. And you can see again that it's a truncated peak. So it looks different. You can see now that the things that are truncated, you can actually kind of see that they have shorter retention times, and they're close to, you can now imagine our scheduling border here at 30 minutes, or a little bit after 30 minutes, and you can see the things that are butted right up against it. So we're seeing a little bit of signal drift. So one thing is we still have these retention times in this logical order, which is our order. We put all the disease on the left and the healthy on the right, and we've got all these, everything grouped by subject ID. But if we want to look at the acquired time order, maybe we'll see a better pattern of what's going on with the retention time. So let's right-click in the retention time plot, choose order, and click acquired time. And so that's the acquired time order. There is this one replicate that's sort of jumping out, but otherwise, I think you get a more of an idea of a progression of the retention times and what's happening to them over time. So, but there is this one replicate that shifts, and I don't know why that is. Air bubble or something. I don't know. Okay, so let's just switch back to order document and move to the next peptide. So this peptide, any evidence that I should do reintegration? Not so much, but you can also see that this is gives me a little pause to be quantifying this peptide. I've got this H159 rep2 active, and I can see that there's something out here which is not my peptide, which is causing some interference. And it's here again at 13.5 or 13.7. There's some other peptide, and in this case, it's my peptide's much more abundant and it's low abundance, but that could change, right? If I'm trying to measure low abundance, this might become most of my signal. It's definitely on which transitions am I seeing it on most? Y6 and Y4, right? So I might, if I really wanted to take this one further, I might winnow down my list by deleting those. And now you can see that there's not quite as much interference. But now I also only have 3 transitions, and you have to think about whether that's enough for you. So okay, well let's move on from that peptide. It is about as well integrated as it can be. Any issues with this one? This is the nicest one we've seen. There is, and actually there's quite a few of these in this document. And in nicer documents, if you've actually gone through refinement, you're going to be choosing a lot of these and hopefully not a lot of the other types of peptides. And you will see a lot, if you get your attention time scheduling such that you're not getting truncated peaks, and if you have internal standards, you'll get even better. And things will be easier to integrate and process. The more your data looks like this, the more you have internal standards, things like that, will make this just a way easier process. But anyway, at this point, you can just go right by this one. Yep, it's integrated perfectly. Although I will call out the fact that there's this one thing that sort of jumps up in this order, because we're going to see that over and over again. So, maybe we would click on it. This is early. We haven't seen that very much yet. We might click on it and see that it's this H146 rep 1, and sure, the peak looks just fine, and so there's nothing going on here, and we can now move on to the next peptide. This peptide's kind of a mess, but when you look at the cases that are okay, it's clearly measuring a peptide. And so if we wanted to do our best to actually, record a measurement for this peptide, what would we do? Yeah. So so we want to try to, so we might just decide, this is not a good peptide and we're not going to keep measuring it. We could delete it. But in this case, I would say we do actually have evidence that we're measuring something, and there's some problems with, you can see this peptide the peak is actually truncated and stuff. But so if we wanted to actually have a measurement for this peptide, we're going to need to fix the peak picking on some of these things. So again, we can look at our retention time plots and our peak area plots And where would you begin? I would begin with the retention time plot here. So I would click on the ones, or not the peak area plot. I would click on the peak areas where it's clearly not the right thing. I would, so actually, so I showed you synchronized zooming. Here again, you could click and then move your mouse wheel to see some synchronized zooming. We could also go to view, and actually maybe some of you are already in this. I don't know. If you were not seeing the peaks close up, was everybody seeing the peaks close up? Okay. So if you weren't seeing the peaks close up, sorry, I didn't start with a blank slate. Then you would want to go to auto zoom, and then auto zoom best peak. And so now this is the most important keyboard command in Skyline. So there are keyboard shortcuts. You can auto zoom none, and then some of you probably were looking at views that look more like this if you were auto zoom none. Or you can auto zoom best peak. And the way to get back and forth is F11 to zoom in and shift F11 to zoom out. And that's pretty useful. Okay, so I'm now looking at H146 rep 1, H159 rep 2, and D103 rep 3. And what I see is the peptide that I'm targeting at 32.9 in H146 rep 1. Next to it is another peptide, something totally different, right? If I zoom in a little bit to that one, I can see that it really doesn't have any signal except for Y4 and Y5, right? So it doesn't have anything on Y8, Y6, or even Y3. So it's a different thing. It's not my same peptide. And that's sort of an interesting quality about this data, is that when you have interferences that don't actually coalute, they can provide a landscape by which you can understand the rest of the data. So now we have this reference point of when we look at these chromatograms, sometimes, or most of the time, we see this other peptide off to the right. So now if we look at these ones where we have no peak, and Skyline has actually in some cases chosen this peak off to the right, what can we know? The main peak is off to the left. We didn't measure it, right? Our scheduling window didn't capture it, and unfortunately, this is the problem with SRM and PRM, and one of the problems that Bruno is really working hard to compensate for with PRM is that I can't go back. So if I want to do retention time scheduling to measure more things, I will end up with mistakes like this, and I can't really go back and get that data. Whereas if I'm doing swath or DIA or even MS1 extraction from DDA data, I can change my window size and look at that peak off to the left. So, but in this case, we really have no other option but to right-click and use remove peak all to just say, yeah, we didn't get a measure for that one. And you can go through most of these ones where we have this. You can see that the relative ion abundance. Now with that knowledge, if you look at this relative ion abundance, you can basically see which replicates chose to integrate this thing, and which replicates chose actually have something like this. There are two very distinct patterns going on here, right? And so we can now pretty quickly click through the ones with the wrong pattern. Yes. And remove peak.
I can see that there are some samples which are facing the same issue, and I would like to remove the peak for more than one sample. Is there a way to do this simultaneously, or do I have to click every?
Like multiple selection? No, there is not right now. We are actually, there's somebody in my lab working on a feature which is apply to all. So where and that's a good point. We should make it work for peak removal too. So we do. This has been a frequently requested feature, and Kaipo Tamura on the team is working on it right now, which would be that, if I wanted to say, for instance, if I decide, oh, actually this one at 35.1, that's the right peak. Now, in order for me to correct that in every replicate, I've got to go do it in every replicate. But we're working on a feature where you can just go apply to all. So we'll do that for peak removal too, and then the next time we talk about this, maybe that'll work. Okay, so, but yeah, for right now, it's not a huge number, but yeah, right now you would have to click on each one. In this case, you can actually see the peak off to the left. So it's a truncated peak, and we could integrate it like that. And I'm not going to make you all correct everything, but I just wanted to sort of show you this data and show you how to do peak removal. And to fully process it, you would just sort of go through and either integrate truncated peaks or remove peaks as appropriate. Or you could just decide, yeah, this is not quantifiable in this case, and I'm just going to get rid of it. So I would go with, retention times, poor retention times, and poor peak area abundance. So again, retention time should be very stable. Relative abundance should be very stable. When you're done with these graphs, they should look very similar. If you come to these graphs and they look like this, you're done, right? And in a lot of cases with good data, this is pretty extreme data where we have a lot of problems. This next one's not even worth correcting. Like it's just too far gone, and if Skyline can't pick, you can see it's very low abundance. We're seeing nothing higher than like 400 or 500. So this would delete. Next one looks okay. The one after that looks okay. Although, again, we might be a little bit nervous about the fact that it's all on Y3, Y4, and Y5. And really it's completely dominated by one transition. But so is our spectral library. So it agrees with our spectral library, but it's not a really good, not a good fragmenting peptide, and we might want to think twice about putting a lot of hope into that. Okay, so now let's go all the way down to the bottom of the document. And at the bottom of the document, we'll see this S protein. And these are the 3 peptides that were injected into this sample. I think they're worm proteins or worm peptides they're not endogenous to this rat plasma, and they were intended to be used as internal standards. So the idea is that we would normalize everything to these, and that would help get rid of systematic changes due to instrumentation and things that we would like to normalize away. So let's look at the bottom one. It looks pretty good. I don't see any reason to reintegrate it. So just in that view, there's not going to be any reintegration necessary there. Same with the one up from that. And then we come to this one. And what do we see? Pretty strange stuff. I'm gonna say that it might look better again if we order by acquired time. So let's right click and order by acquired time. And now we can see more of a pattern, right? Before it looked kind of random and strange. It still looks pretty strange, but okay. So if you look at a lot of these, you'll actually just go like, oh, I know what that is. Does anybody know what that is? There's maybe degradation, but yeah. So we're seeing this Y4 and it's getting bigger. So what does that tell me? Actually, you can see it right here. Signals going down and there's interference. So we're getting more variability because signals going down, So you can guess these things before, like we're going to look at this by removing the normalization and see what we see, but you can start to get, I've seen this kind of pattern a bunch, and it usually means that signal of my peptide's going down and there's interference from another peptide taking over. So when I have hot, this may be the same interference here, because this is, 10,000 and this is, 3,000. So I don't know. But anyway, so that interference is around in a lot of these, but when the signal's very high, it doesn't have a huge impact. When the signal goes down, it has a much bigger impact. If you right click on this graph, the peak area graph, and click normalize to none, then you'll see that this is the peptide that I've been showing you that had 200x signal degradation. If you right click here, you could go look at log scale, and that would help you see this, going from 2 to the 6.5 down to, or 10 to the 6.5 down to below 10 to the 5. So it's 200x signal degradation. You can trust me on that. Turn off log scale again. Okay, so now, so this is clearly not, actually now that we've got it unnormalized, let's look at the other peptides too. So this one is the one that I'm saying is probably fairly similar to a lot of my peptides. And I guess, how might I get a view into that? I took technical replicates, right? So I should have, so I'm saying that my hypothesis here is that there is some signal decline over time in this experiment for all my peptides. Then it's going to be sort of similar to this, but not really like 200x difference. So the way I can look at that is I'm going to sort back into document order. So right click on the peak areas and go document order. And now you can see this sort of stair-step pattern across my replicates. 1, 2, 3, 1, 2, 3, 1, 2, 3. So you see this diagonal decline. And now if I go and look at some of my other peptides, let's see. You can see this. You can see a similar decline, and you have to look in triplets because these are biological subjects. So we're not expecting them all to be the same. But if you look at triplets, you can see that frequently there's a decline going from forward to backward. So yeah, this one too. So yeah, see. So that's an indication that the same thing that I'm seeing in here is repeated in my subjects or in my actual analyte peptides. So in this case, these 3 peptides are all injected into the sample at a constant concentration. Their total intent is to catch this sort of decline. Okay, let's look at the last one and figure out whether it would be a good normalization peptide. Whoops. Let's sort back into acquired time order. And you can see that it has considerable decline as well. Probably more than is explainable by, this is probably some sort of degradation or something going on. This is about a 20x decline from the earliest to the latest. So neither of these are probably good, for normalization. So we can let's go ahead and right click on the middle one. Yeah.
Could you compare this to the total ion current of all?
Yeah, so why is that a bad idea in targeted proteomics? But why? No, that's an important point. Why is it? So why do we inject peptides at all? Why don't we just do total ion current with a targeted experiment? It's a very common thing to do in a DDA experiment, right? So why? Too little peptides? Well, what do we expect of these peptides? Where do they come? They come from like the literature. On this case, we're expecting them all to change, right? So when we normalize to total ion current or to the median peptide or something like that, we're assuming that the vast majority of our data is unchanging. Whereas, in this case, the whole point of this experiment is we hope that everything is absolutely everything is changing. So there are normalization strategies that we might, if we adopt them from DDA, we might actually normalize away our entire effect. And then we'd be like, oh, nothing changed. But
What I want to say is that on your reference peptide, when you see they decline, or
yep.
decline less than the other, if you normalize it to the total ion current on those peptides.
That's basically what we're going to do. Yeah. So right click on this peptide. So the hope of the person who wrote this experiment was that we would select all three of these peptides and do what we're going to do for the one. But after assessing the data quality, we're going to go. We're just going to take the one. And ideally, in this sort of cycles of refinement, someone would have done this experiment before acquiring all the data to verify ahead of time that these were going to be good normalization peptides. And that's, this is one of our earliest experiments. We're learning too, but today we would do the degradation experiment 48 hours, apart, and make sure that we don't have degrading peptides. Okay, so right click, standard type, and then choose normalization. And when you do that, you'll see this really minuscule little % sign appear right next to the peptide, and that means that it's a normalization standard. And now, if we want to see the ratios that we're getting for the other peptides based on the total ion current of that peptide, or any other we could do it for all the peptides, and maybe we will in just a second. Let's expand the next peptide up from S, and you can see that there's no ratio reported here. And what I need to do to get the ratio reported is to click in the targets view. Right click in the targets view, sorry. So right click in the targets view and then choose ratios to, and it currently says ratios to heavy. Well, we don't actually have any heavies, so we want ratios to global standards. And now you'll see that I get a ratio actually for the precursor and the transitions. And what I would hope is that the transition ratio should be fairly constant. Right, so they're relative to each other. They should be fairly similar. Does that make sense? No, that doesn't necessarily make sense. The ratio would be constant if we had a reference standard, but not in this case. Yeah.
So what does it do now? It takes every
and divides it by the total of this peptide. So they shouldn't necessarily. I think they should not necessarily be. Yeah, they're not necessarily similar. But if I have a reference standard, then they should be equal. Yeah. Because again, the ratios are dependent on what the active replicate is. So it's just showing you the ratio for. It can't show you the ratio for every single peptide. So if you now activate H147 rep 1, you'll see exactly the same ratios as me. So so if I wanted to see all the ratios, then I can go to this document grid or the result. Actually, we can go ahead and maybe try the results grid. So view results grid. This gives me a grid. And it's showing me a ratio to standard, but that's not the right ratio to standard. That's ratio to my heavy again. So if I want to go ahead and get the ratio to the global standard here, I would go views, customize view, and then way down here I've got ratio light to global standards. And if I check that, and I'm going to also select this ratio to standard and click this X to get rid of it. So then, and we're going to call this peptide results ratios. So we're creating a custom view here for our results grid where we have replicate, peptide peak found ratio, peptide retention time. I guess I don't really care about this peptide peak found ratio either. So just 3 values: replicate, peptide retention time, and ratio light to global standards. And then if I click OK, that will now give me those ratios in here, and I can see the ratios for, unfortunately, I could choose to dock this over on the side here, and that might be okay. And I could then unpin it again, and now I have this thing that shows me most of my ratios across all replicates in a fairly quick view that I can pop up. Yeah.
Same function like is available when I go to File, Export, Report.
Similar. This is actually. I'm going to repin this. This view is sensitive to the selection. So if I click up to the next peptide, you'll see that I get all of its retention times and its light to. So it's a selection sensitive thing. It's also got it's got links that you can click on to activate certain graphs. So that's the results grid. The big difference between the results grid and the reports is that it's selection sensitive. So I'm going to unpin that again. The thing that's most like the reports is the document grid. So you would go to View Document Grid, and then this would show you information across the entire document. And this is the protein view, showing us all of our proteins. I'm just going to close that up again because we're not going to work with that. Okay, so, yeah. 15 minutes overtime already. So guess what? We've got another Sky Jam later, so we're just going to stop here. But anyway, so that's I think we'll pick up with this data set next time. I think it's a great training ground to learn a lot and to actually see how you can sort of go through these processes of processing things, but Skyline also allows you to sort of just launch into directions of inquiry that are driven completely by you, get to information very, very quickly, and I mean I liken it a little bit. I was at a conference, and somebody had done a presentation where they said, oh, there's all this imaging data, and we're going to make this amazing platform that just does all this amazing stuff. That'll be a black box, and that will just give everybody a report. And then I was asked by Olga Vitek, who's going to be talking tomorrow, like, how does that differ from Skyline, and why do it was supposed to be on reproducible research, and what is it about Skyline that makes it easier to produce reproducible research? And I would say that this ability to really drill in and understand what was going on is important, and no matter how big your data is. And so then I do the comparison to Google Maps, right? Huge amount of data about the world, but I can go, oh, I want to go look at what my neighborhood looked like when they took pictures, and I can get there very quickly. And so our attempts in Skyline is to create that same kind of atmosphere where you can go, whoa, why does that look a little weird? And you can get from that matrix grid of just a bunch of values into the actual data very quickly. And so I'll leave you with that, and we'll get more into some more exploration. There's lots to be explored about this data, and we've just started. So thanks.